today on How It's Made. Ball bearings, electrical wires, lost wax casting, and automated machines. With all the high-tech hoopla these days, the lowly ball bearing gets forgotten. Yet machine parts need ball bearings to rotate. They're in household appliances, industrial machines, and car engine parts such as alternators and fans. This is what's called a deep groove radial ball bearing. It has steel balls that move inside tracks called raceways. The raceways are carved into a set of heavy-duty steel rings. The balls are made of the same type of steel. They first prepare to shape the rings to the right thickness. They insert the inner ring into the outer ring. The set then passes through a grinder that alters the width to the correct thickness. A gauge checks the width of each ring as it exits. Now they separate the inner and outer rings in order to grind their outer circumference on separate machines. The outer ring enters the grinder, which shapes its outer surface to a precise roundness and diameter. A water-based liquid keeps the ring from overheating, which would cause warping. The ring exits the grinder through a gauge that checks the diameter. Next, the outer ring's raceway goes for grinding. Abrasive stone wheels with an oil coolant shape the surface to precisely the correct roundness and size. The inner ring and raceway go through a similar machine. Now the rings go for polishing. An abrasive stone lubricated with oil polishes the steel surface until you can see a reflection. Here's the before and after. Next stop, washing. They coat the rings with thick oil and a fine stone grit. They clean the raceways with kerosene. Elsewhere in the plant, they classify the steel balls according to size. These balls started out as steel wire. A machine cut them into pieces, and a die punched them into rough balls. Those rough balls go into a grinder which removes the bumps. Then other machines round them out and give them a mirror finish. This entire process takes a few days. The balls go through a furnace to harden. Then they get a bath in cleaning solvent. After several quality checks, the finished balls go into hoppers. The hoppers load onto the automatic assembly machine. The ball feeder sends balls down through tubes to a ball pusher that feeds the correct quantity of balls into the raceways of the now reassembled inner and outer rings. A ball divider positions the balls evenly around the raceways. Next comes the ball cage, a metal cage that retains the balls in position around the raceways. The first machine installs half of the cage, the half with rivet holes. The next machine carefully positions the other half of the cage, the half with rivets. The machine test spins the bearing, then rivets the two halves of the ball cage together. The bearing is now fully assembled. Now it goes into a solvent bath, then for a series of automated quality control tests. This noise vibration tester makes sure the ball bearing operates quietly. Some types of bearings are lubricated with grease. A machine squirts grease evenly into the bearing's raceways, then inserts a rubber seal to contain the grease. A final quality control test. An automated scale tosses out any bum bearings that aren't the required weight. The good ones move on to the laser, which marks them with information such as the part number and the trademark. What is genetically modified food? Scientists manipulate the genes in crop seeds to increase yield or to make the crop more resistant to disease or insects. There's a worldwide debate over whether this manipulation of nature poses a risk to our health or to the environment. We're so used to them that we barely notice that electrical wires are all around us. They're in aerial and underground cables running along our streets and to our homes. They're behind our walls and inside our electrical appliances. To make color-coded electrical wires, they use what's called rod, made of either solid copper or solid aluminum. They feed the rod into a machine that draws it out through a series of lubricated pulleys and dies, stretching, lengthening, and thinning it out. And eventually winding it onto a large bobbin. What was once a rod 10 millimeters in diameter is now down to just 2 millimeters, the width of about a dozen human hairs. They load the bobbin into what's called a stranding machine. They cold weld the end of one bobbin to another, guaranteeing an uninterrupted flow once they start up the machine. At high speed, the stranding machine twists 7 wires together, forming an electrical conductor, also called a bare conductor. This is a low-voltage conductor, under 1,000 volts, the kind you find in the cables that run electricity from the hydro pole to your home. Bare conductors need to be insulated so people handling them won't get an electric shock. A plastic extrusion machine coats the conductor with polyethylene or PVC. This insulates the conductor. This is what the polyethylene looks like in its raw form. As the conductor exits the machine with its new insulation, a precision laser gauges the diameter to make sure the insulation is uniform and the right dimensions. The extrusion process has heated up the conductor, so it has to be cooled down with water. Sometimes 2 or more conductors are twisted together. When that's the case, a printing machine applies a white stripe to identify which is which. The client who's ordered the conductors specifies the colors of insulation. It chooses them based on how it wants to color code its electrical wiring. Several conductors are often grouped together to form a cable. The plant performs a voltage test, immersing the cables in water to make sure they don't short circuit. These medium voltage cables can carry from 1,000 to 46,000 volts of electricity. They're the type used for underground hydro lines. They're insulated the same way low-voltage cables are. The plant prints the date of manufacture, the voltage, and any other information the client has requested. The cable then goes onto a reel to be tested before it's shipped out to its destination. In the middle of the cable, surrounded by copper grounding wires and a host of other components, is the heart of the electrical cable, the bare conductor. Many machine parts are simply stamped or machined out of solid metal, but parts with complex shapes or thin walls can't be made that way. They have to be cast using a technique called lost wax process casting. It takes anywhere from a week to a month to manufacture a cast metal part, depending on its complexity. The first step is to inject wax into an aluminum die, which is essentially a mold whose cavity is in the shape of the part. This creates a wax model slightly larger than the finished part will be. They'll use this wax model to make a mold out of a ceramic material. That also has to be larger than the finished part because metal shrinks as it cools. Once the wax model is ready, they stamp on a code to tell the foundry workers what type of metal to use to cast the part. Next, using a hot iron, they attach wax components to create what's called a metal delivery system, channels that will funnel the molten metal into the mold's cavity. Next, they dip this wax assembly into a ceramic solution called slurry. They do this by hand to prevent imperfections that would cause defects in the casting. To strengthen the slurry, they coat it in a fine zirconium sand, then let it dry. A robot then keeps repeating the process with coarser sand until the ceramic shell surrounding the wax assembly is about 7 millimeters thick. This takes 5 days. Now the ceramic-covered wax assembly is ready for what they call the de-wax. Workers place it in a hot steam chamber called an autoclave for 5 to 10 minutes. This melts the wax right out of the shell, creating a ceramic mold whose cavity is in the shape of the part. Once the mold has dried out, workers can begin to cast the part. First, they put the cold mold into an oven and heat it up for 2 to 3 hours. This prevents the mold from cracking from the shock of coming into contact with molten metal that's a piping 1200 degrees Celsius. They pour the metal into the mold's cavity, then let it cool and harden at room temperature. That takes 2 hours for aluminum, 4 to 5 hours for steel. Once the metal has cooled and solidified, they break off the ceramic mold using a vibrating hammer. This takes about 5 minutes. They saw off the metal delivery system, then grind the surface smooth. The final step is to make sure the part came out to the exact dimensions specified in the technical drawing. This is called sizing. Steel parts have to be heated up in an oven for sizing. Aluminum parts are sized cold. Technicians use a series of tools and presses to measure the part. If it doesn't meet specifications, it's either reworked or simply discarded. They use sophisticated equipment such as this optical comparator to check angles and radiuses, and this coordinate measuring machine to verify dimensions. Lost wax process casting is used to make metal parts for all types of machines and equipment, everything from military weapons to snowmobiles. Since the Industrial Revolution, manufacturing has become increasingly automated. It's about time How It's Made paid tribute to that marvelous feat of engineering, the automated machine. Until the 1780s, goods were made one by hand in a home or workshop. Then came the Industrial Revolution, the mass production of products in huge factories. Industry's next revolution was automation, made possible by computer technology. By the 1970s, 2 centuries after the start of the Industrial Revolution, robots began replacing humans on the production lines. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.